Hi everyone, thank you for joining us. I'm Trish McLean, the marketing person at Mirus, and we're happy to have people from all over the world joining us for today's webinar, How Harmonics Have Led to 6 Power Factor Misconceptions. Our presenter today is Tony Huvenaar. He is the president and CEO of Mirus International and a professional engineer. Tony joined Mirus in 1996, having previously held the position of Chief Facilities Electrical Engineer at IBM. Tony has over 30 years' experience dealing with issues caused by harmonics, and he has gained valuable insight in the resolution of power quality-related problems. He has published and presented numerous technical papers on power quality and harmonics, and we're very happy to have him with us today. A few logistics for today's webinar. Because we have many people on the line, everyone's sound is muted. Please send your questions in through the chat console or through the question box, whichever you prefer, and we will answer questions at the end of the presentation. The presentation will be about 30 minutes with questions to follow. For those of you who require documentation for professional development hours, please email us at mirus@mirusinternational.com. The address will be at the end of the presentation, and we will send you a certificate of participation and a test following the webinar. And with that, I'll hand it over to Tony.
Thank you very much, Trish, and good day, everyone. This is our second webinar session for this topic on power factor misconceptions. And I'm extremely pleased that we are once again have such a large audience. I know that some of you were originally signed up for the initial session, but were unable to log on. I apologize for that inconvenience, and thank you for taking the time again today to join us. Mirus has been assisting customers with treatment of harmonics since our inception in 1991. And with this experience, we have found there to be a general misunderstanding of how power factor is affected by harmonics. So I decided to write a white paper on the 6 most common misconceptions. The white paper is available for download from our website, and the webinar today will provide further insight on this topic. Although a low power factor does indicate that a power system is not being effectively utilized, if this occurs only when the system is lightly loaded and the reactive power component in kVAR is quite low, there is no need for concern. Only when the power factor is quite low under more heavily loaded conditions does it need to be addressed. Placing conditions that are too rigid with respect to power factor can lead to installations that are more complex, costly, and unreliable than necessary. And in many instances, a little leading power factor can be effective in compensating for inductive reactive power located elsewhere on the power distribution system. Today we'll be discussing power factor in the power triangle, the 6 power factor misconceptions, how the harmonics generated by nonlinear loads affect power factor, utilities, power factor penalties, power factor correction capacitors and the potential for resonance with the power system, how passive harmonic filters can improve power factor, and the effect of leading power factor and capacitive reactance on generators. For those trained in electrical theory, the concept of power factor used to be fairly simple to understand. Power factor is a measure of how effectively a specific load consumes electricity to produce work. It's the ratio of real power in kilowatts to apparent power in kVA. The higher the power factor, the more work produced for a given voltage and current. Power triangle shown on this slide, though, applies only to linear loads. And it shows inductive reactive power component in kVAR, inductive or capacitive, upwards being inductive, downwards being capacitive, the real work component in kilowatts on the x-axis, and then the vector sum of these two powers results in the apparent power or kVA. Power factor being real power over apparent power is equal to the cosine of theta. And also apparent power can be represented as the square root of the real power squared plus the reactive power squared. The 6 misconceptions of power factor, with the first being that low power factor is normally caused by electric motors and other inductive loads. Although it is true that inductive loads consume reactive power and thereby reduce power factor, with today's proliferation of harmonic generating power electronic nonlinear loads, low power factor is now most often caused by harmonics. The second one is low power factor can always be corrected by adding capacitance. If low power factor is due to harmonics, treating with capacitors can often make the problem worse. Third is power factor must always remain high to prevent power factor penalties. Although there are many different ways that power factor penalties are applied by utilities throughout the world, they almost universally apply these penalties during periods of peak demand. Therefore, if low power factor only occurs under lightly loaded conditions, it will not result in power factor penalties. Fourth one is that harmonic filters must always be equipped with contactors to switch out capacitors under light loading conditions. Many harmonic filters do require switching out contactors under light loading, but a properly designed one does not have that requirement. Fifth is that leading power factor is a problem for generators under any condition. It is true that a leading power factor that results in high levels of capacitive reactive power is a problem for synchronous generators, but in certain conditions, power factor can be low and leading without there being too much capacitive reactive power for the generator. And finally, it's just a simple statement that any leading power factor is bad. We often hear this from people, and a leading power factor can be useful in compensating for a low lagging power factor. Therefore, as long as we ensure that the capacitive reactive power is not too high, it is not always a bad thing. So when we consider power factor with nonlinear loads that are introducing harmonics in the power system, these would be loads such as 6-pulse rectifiers and other thyristor type bridges and conversion, basically power electronics that converts AC to DC. These rectifiers don't typically shift the current, but they distort it. So harmonic currents that are generated do no useful work and therefore contribute to reactive power. The power vector relationship becomes three-dimensional. We still have an inductive or capacitive component. As before, we have the real power component, but we now have a third or a second reactive power component, which we refer to as distortion reactive power. And this is 90 degrees out of phase with the inductive or capacitive component and 90 degrees out of phase with the real power. The apparent power now that this power system has to deliver is the sum of all three vectors: the real power, the inductive or capacitive component, and the distortion component. So power factor is still real power over apparent power, or kilowatts over kVA, but it no longer equals cos theta. Cos theta now is referred to displacement power factor. Our apparent power now is the square root of all three components: real power squared, reactive power, that's inductive or capacitive, Q squared, and the harmonic distortion component, H squared. So true power factor now is equal to the displacement power factor, dF, which is equal to cos theta, times the distortion power factor component, or HPF. To show this relationship, I've created this table which provides some values for a typical nonlinear load. So in this table we've got our harmonic component. We show the odd harmonics, because those are the ones that are most predominant in our power systems. Then we have a column with the harmonics as a percent of the fundamental component. So, and this is typically the way harmonics are measured or indicated in North America, South America. There's also a percent RMS value that we show, and that's typically used in Europe and other areas of the world. In this column with percent fundamental, the 60 hertz or 50 hertz fundamental component is going to be 100%. It'll always be 100% of the fundamental component by definition. Third harmonic here we're saying is 70% of the 60 hertz or the 50 hertz fundamental component. Fifth harmonic's 35%, seventh is 20, and so on. Our total harmonic distortion, which is represented by the square root of each harmonic squared, and the sum of those, take square root, and then we divide by the fundamental component. That measurement is 83% with this load profile. The same load profile, though presented as a percent of RMS, has 77%, the fundamental being 77% of the total RMS. The RMS total is here is 130%. 54% third, 27% fifth, for a total THD of 64%. We also have an I squared H squared component, and this is the factor that is used to determine our K rating, which is a measure of how well a transformer, essentially the extra heat generated by the load due to the harmonics, and it represents how a transformer can handle the nonlinear loads. So we have a K factor rating for this load profile, which is equal to 9, which is the sum of all the I squared H squared relationships. And then our power factor, in this case, is the distortion power factor component. So it's a component that's introduced by the harmonics, is equal to 1 over the square root of 1 plus the total harmonic distortion squared. So in this case, it's 0.77. So we have a very low power factor, and this very low power factor is due to the harmonics introduced by the nonlinear load. To show this in another way, I've got some waveform representations of 4 different types of loads. Here we can see for a 6-pulse diode bridge rectifier, pulse width modulated variable speed drive, we have the typical double humps of pulsed current. So this is not a sinusoidal current. Being non-sinusoidal, it contains harmonics. It's got a 5th harmonic component, 7th harmonic, 11th and 13th, predominantly the odd order harmonics. The total harmonic current distortion of this waveform is 73%. The power factor, power factor is 0.79 lagging. When we add a 3% AC line reactor to this same variable speed drive, it broadens the current pulse slightly. By doing that, it makes it a little bit more sinusoidal, which lowers the current harmonics. In this case, we've essentially dropped the current harmonics in half. So we now have about 35% THD. So line reactors can lower the harmonic content, but they are limited in their effectiveness. Power factor now is increased to 0.9 due to the reduction in harmonics. Many drive manufacturers will offer phase shifting multi-pulse drive systems. 12 pulse, 18 pulse are very common. The 12 pulse system is shown here. We can see the current now due to the phase shifting and canceling of harmonics that's introduced by that is again more sinusoidal. There is certainly residual harmonics in the power system. In this case, we're at 9.3%. This is a very good functioning 12 pulse drive, and power factor is improved to 0.98. The 6-pulse variable speed drive shown here in combination with a passive harmonic filter that we offer, the Lineator, will result in very sinusoidal current, very low harmonic content. Here we have 5.8% current distortion and essentially a unity power factor. So typically with power electronic loads, the displacement power factor will be near unity. The true power factor can be quite low, though, due to the distortion harmonic component. So if we remove the harmonics, we will restore the power factor to near unity. So the first misconception is that low power factor is normally caused by electric motors and other inductive loads. when in reality, low power factor is most often caused by distortion, reactive power, introduced by harmonic generating power electronic nonlinear loads. Now let's take a second and look at power factor penalties. So most utilities charge their customers for the energy supplied in kilowatt hours during the billing period, plus a demand charge for that period. And demand will equal the peak kilowatt load during a set period, and often that period is 15 minutes, and it's a sliding 15-minute window. If power factor is low, then lower than required by the utility, which often the utilities will require a 0.9 or a 0.95 as a minimum power factor, then the utility may also apply a power factor penalty. An example of this would be if the minimum utility power factor was, say, 0.9, but the actual load at the facility was 800 kilowatts of real power, but 1,000 kVA of apparent power, which would be a power factor of 0.8. The utility would charge the customer as if the demand were 0.9 times 1,000 kVA or 900 kilowatts. So what they do is they take the apparent power value and multiply it by the minimum power factor that they will allow. That would result in a penalty of 100 kilowatts in this case. If the demand charge was $10 per kilowatt, it can vary quite dramatically, but $10 is a fairly typical level, then that would be a penalty of $1,000 per month. So a fairly significant addition to a power bill. Improving the power factor to 0.85 at 800 kilowatt demand would lower the penalty to just 47 kilowatts or $470. This is because the 800 kilowatt demand divided by 0.85 power factor is a 941 kVA. So the load would then only draw 941 kVA. If we take that 941 kVA and multiply it by the minimum demand or minimum power factor of 0.9, the resultant kilowatts is 847. So that's 47 kilowatts above the 800 that we're actually drawing. So for power factors that were in the range of 0.92 unity, above the minimum, there would be no power factor penalty. And one important item to note here is that if the low power factor appears only under lightly loaded conditions, it will not affect the demand charge, because the demand charge, by definition, is applied when we're at peak demand load. So misconception number 2 is that power factor must always remain high to prevent power factor penalties, when in reality power factor penalties are only applied at times of peak demand. Therefore, low power factor during light loading conditions has no consequence. Now, if we have a low power factor and that low power factor is a result of an inductive reactive power, so maybe fixed speed motors or other inductive type loads, then we can apply power factor correction capacitors to improve it. The example I'm showing on this slide, we have again 800 kilowatts of demand, real power demand load. We have 600 kVAR of inductive loading requirement. And the combination of two vectors results in apparent power of 1,000 kVA, and this is indicative of a 0.8 power factor. So if we want to improve the power factor, say the utility has a minimum power factor of 0.9. We want to improve it to a safe level, so we've chosen 0.93 as our design level to improve it to. Then the apparent power, the resultant apparent power, would be the 800 kilowatts divided by 0.93, so it needs to be 860 kVA. If we apply our equation for reactive power, then we take the apparent power, our design apparent power squared, subtract the real power squared, and we can only have 315 kVAR of inductive reactive power. to maintain a 0.39 power factor. So that would require a capacitive reactance that's equal to the inductive reactance prior to application of the capacitors minus our design reactive power, which means 285 kVAR. And then we will end up with the vector shown below. The problem is power factor correction capacitors are often misapplied these days because the low power factor is the result of harmonics introduced by nonlinear loads rather than the harmonics introduced by fixed speed, or sorry, rather than the inductive reactive power introduced by fixed speed motors. So here in this vector configuration that I'm showing, we have a fairly small Q, or inductive component in kVAR, but we have a quite large H, which is our distortion component. This is very typical of nonlinear loads. In fact, this is often much smaller than I'm even showing here. The vector sum shows our apparent power configuration. So here, the only way to improve the power factor and reduce the apparent power is to reduce our distortion component. And that requires harmonic mitigation equipment. Misapplication of power factor correction capacitors can lead to overcompensation and resonance with the power system if they're applied when the low power factor is due to distortion. Power system harmonics results when the harmonic generating loads, the current introduced by the harmonic generating loads, are subjected to a power system where the capacitive reactance is equal to the inductive reactance at a certain harmonic frequency. This simple single line diagram we're showing here has a source and a source reactance, XS. We have a nonlinear load, which could be a variable speed drive injecting harmonics into the power system. These harmonics pass through, say, a transformer and its impedance into the bus where we have connected in parallel power factor correction capacitors. And then we also have all of our other loads in the system, which might be fixed speed motors that have an inductive reactive component. The equivalent diagram of this one line is shown here, where we've got our current source of harmonics, which is the variable speed drive injecting harmonics into the power system, pass through the transformer's impedance in series, and then they reach a parallel combination of the reactive power of the power factor correction capacitors and the resultant reactance of the power system. And that would be the combined parallel reactance of the source and other loads on the power system. Very difficult to calculate in a lot of cases, but it will have a component, and it is almost always inductive. We resonate when the reactive power of the power factor correction capacitors at a certain harmonic is equal to the reactive power, inductive reactive power of the system at that harmonic. So here we have our inductive reactance curve, which equals 2 pi FL. We have our capacitive reactance curve, which is equal to 1 over 2 pi FC. And at this particular point, we have our resonance frequency, because the combination of the two reactances is equal to 0. With 0 reactance, there's very little impedance to the flow of this harmonic. This would be our resonance frequency, which is equal to 1 over 2 pi root LC. So now, if we have harmonics that are introduced to the system at that resonance frequency, a very little bit of harmonic voltage at that harmonic number will introduce and produce circulating currents between the power system components and the power factor correction capacitors. And these circulating currents will flow, and as they flow, they create voltage drops, which increases the voltage, harmonic voltage, which then drives more current, and that would increase infinitely, except there is some resistance in the system that's going to dampen that resonance somewhat. But eventually it'll settle down, but we'll end up with very high current and voltage distortion levels, which can result in destroyed capacitors and fuses protecting those capacitors, can damage surge suppressors on the power system, be it at the transformers or at sensitive equipment. Can result, if the voltage distortion is extremely high, can result to failure of a connected equipment, and in extreme cases can result in power system shutdowns. An example of power system resonance is shown on this slide. Here we have an oil field in Midwest USA where they used a lot of electrical submersible pumps, or ESPs. These pumps were used to help push the oil up as the oil field was reaching its end of life, and so they're trying to get as much oil out as they could, and so they're using, there's not enough pressure to drive the oil up, so they were using the pumps to push water and introduce the pressure. The power factor was found to be low by the utility, so the utility insisted that the oil company install or pay for the installation of power factor correction capacitors at the utility substation. But those power factor correction capacitors actually made the situation worse because the voltage distortion, they resonated with the harmonics generated by the electrical submersible pumps, and that drove the current distortion and voltage distortion up higher. So when we were asked to investigate the site, we saw that the voltage distortions were extremely high, figured that that was due to a resonance condition, asked the utility to start switching off the cap banks and see what effect it would have. So they had two switchable cap banks. When they turned one of the cap banks off, the voltage distortion dropped to 11 to 12% range. Current distortion dropped to the 18 to 20% range. When they turned off all the capacitor banks, it then dropped to less than 9% voltage distortion, still higher than we want to see as 5%, but certainly much lower than our starting levels. And you can see there was very little impact to power factor. And this was because the majority of the reactive power was harmonics. So we were able to convince the utility to keep the power factor correction capacitors off, and then we introduced harmonic filters on all the electrical submersible pumps to drop the current distortion further and lower the voltage distortion and improve the power factor. So misconception number 3 is that low power factor can always be corrected by adding capacitance, when in reality, if low power factor is due to distortion reactive power, adding power factor correction capacitors will not only be of minimal benefit, they may very likely make the harmonic problem worse by resonating with the power system impedance. But one solution that can be effective in improving power factor when we have a lot of nonlinear loads is passive harmonic filters. Having a properly designed harmonic filter, however, is critical to ensuring that harmonic mitigation meets the targeted levels without introducing excessive capacitive reactance under lightly loaded conditions. The large capacitor banks of conventional trap filters and most broadband filters present a high capacitor reactance to the power system, which can raise voltages or cause excitation control problems in generator application. Mirus offers a passive harmonic filter known as a Lineator, which is an input filter for the variable speed drives and treats the entire spectrum of the harmonics generated by the VFDs. It will provide performance better than 18 pulse when applied to a 16 pulse VFD. We guarantee that IEEE 519 harmonic limits will be met with current distortion being less than 8% regardless of the short circuit ratio and voltage distortion less than 5. We have models available that will provide less than 5% TDD in any application, and occasionally those filters are required with very sensitive loads are involved. But by treating the harmonics, we will restore the power factor to near unity We ensure compatibility with generators by limiting our capacitive reactance to less than 15% of the rated kVA of the load. We're the most highly efficient of all the passive filters on the market. The key is in the design of our reactor, being a multiple reactor on a common core, shared yoke configuration as shown here. And we have sizes that range from 5 horsepower all the way up to 3,500 horsepower. The connection diagram of the Lineator passive filter is shown here. We have a blocking reactor, very high impedance on the input. We have a compensating reactor on the output where the load is connected. And we have our branch reactor, which combines with our capacitors to produce our tuned frequency. And this unique reactor is designed allows for the design of a smaller cap bank to reduce voltage boost and reactive power at no load. On the input side, we make sure that we're tuned below the 5th harmonic, safely below the 5th harmonic. So therefore, Harmonics pre-existing or existing background distortion that's a result of other loads on the power system will not be imported into the filter. And then on the output, it's tuned above the 7th to be most effective in filtering out the harmonics generated by the variable speed drives. As I mentioned, we designed to have less than 15% capacitive reactance. So this graph shown here is for a 300 horsepower filter, or 480 volt filter, but is typical of all of our filters that we offer. Here we can see we have the leading reactive power in kVAR as a percent of the full load kilowatts. And on the right side we have, on the left side is leading power factor, and on the right side we have lagging power factor. The y-axis is our loading. And at no load, we're at 15% or less. As we start to load up the filter, the capacitive reactance drops. Well, at 60%, we introduce no capacitive reactance, and then we become inductive as we continue to load up the filter. So we will guarantee less than 15%. Competitive filters are typically in the 35 to 40% range. Why is that a problem? Well, when you're in the 35 to 40% range, you end up being outside the generator reactive capability curve. So this is a typical generator reactive capability curve. Here again we show reactive power leading on the left side, lagging on the right side, loading on the y-axis. The various power factors of the loads, radial curves coming out from this center of that graph. As long as the load on the generator is within this envelope, the generator can handle the reactive power without incident. So we can see that for lagging loads or inductive loads, generators can easily handle very low power factors, very high levels of reactive power. But on the capacitive side or the leading side, this particular one actually can handle 20% maximum at no load. That increases a little bit as we start to load and then has a kind of an awkward curve here. But since the capacitive reactance of the filter is highest at no load, the no load requirement is the one of most concern. So we can see here other filters are outside that envelope. So if a generator, this generator was loaded with variable speed drives that were filtered with passive filters of these competitors, the generator would struggle with its excitation control, whereas the Lineator is comfortably within that envelope. So misconception number 4 is that leading power factor is a problem for generators under any condition. Although it is true that generators typically handle inductive loads better than capacitive loads, They are capable of handling a leading power factor load provided the capacitive reactance remains within the generator's reactive power capability curve. A harmonic filter with less than 15% maximum capacitive reactance will meet this requirement. Therefore, if you have a filter of this design, you do not require switching out of the capacitors under light loads. But if it's above the 15% or typically in the 30 to 40% range, you will require those contactors. I also show the power factor of these passive filters. Here again we have loading on the y-axis. We have lagging power factor on the left side, leading power factor on the left side, lagging power factor on the right side. Total power factor remains high for our Lineator filter in the operating range from 0.95 or greater than 0.95 in 30% and higher. So we're actually typically in around even almost approaching 20% loading levels. We're above the 0.95 power factor. We are leading under lightly loaded conditions, but then we end up being lagging as we reach 50% load and up into the higher loading levels. The leading power factor at light loads is of little consequence since capacitive reactance in kVARs are kept low. There's little voltage boost. We're compatible with the generators. We will not introduce power factor penalties because this is only at light loads, and no contactors are required to switch out the capacitors. Again, as I mentioned earlier, other filters will remain leading until much heavier loads are reached and therefore will require cap switching contactors. And one of the things that our filter does is that helps protect the variable speed drive from high switching transients such as power factor correction capacitors, utility power factor correction capacity switching, or in this particular case it was due to the notching introduced by large thyristor bridge rectifiers on an oil platform, drilling platform, an offshore oil drilling platform. And what can happen is when you have these notches, you can get ringing, which can result in overshooting and additional ringing effect. So you can see that there's a high voltage peak on the input of our filter, but on the output of our filter, that ringing and overvoltage is totally removed, and the variable speed drive will see much cleaner voltage, and it does help protect the variable speed drives. We've run into situations where people have insisted on putting contactors on the Lineator filter. They lose this advantage because if they're switching out the contactors under light loads, if that's when the power factor correction capacitor switching occurs, then these overvoltage transients will pass right through and affect the downstream equipment. So misconception number 5 is that harmonic filters must always be equipped with contactors to switch out capacitors under light loading conditions, when in reality a properly designed passive harmonic filter with less than 15% maximum capacitive reactance as a percent of the kVA rating does not require a contactor to switch out capacitors at light loads. In fact, keeping the capacitors in the circuit can help protect the VSD from overvoltage transients. And then the final misconception is simply that any leading power factor is bad. In reality, there are many conditions under which a leading power factor will not cause problems. In fact, if the other loads on a power system are inductive, introduction of some capacitive reactive power can be a good thing, as it could provide some compensation to improve overall power factor. So then in summary, we now know that harmonics generated by nonlinear loads have led to many power factor misconceptions. In reality, low power factor is often caused by harmonic generating nonlinear loads rather than inductive loads. Power factor correction capacitors are not always the right solution for low power factor, and they can introduce system resonance issues. Power factor must be high during peak demand loading to prevent power factor penalties, but can be low at light loading conditions. Properly designed harmonic filters do not need capacitive switching contactors. Providing that reactive power remains within a generator's reactive power capability curve, it can handle a leading power factor load. And finally, low leading power factor is not necessarily a bad thing, as long as the capacitive reactive power is low. So I thank you for taking the time to join us through this webinar. We now can entertain some questions if there are any, if you want to type those in, and we'll see if any came in during the seminar. One question that's come up is we're asking if we've had any problems, applications involving generators and our filters. And provided the total Lineator load connected to the generator does not exceed the generator's full load rating, we have never had a problem with the generator. If we have a connected load is much larger than the generator, in some cases that still will work, but if it's excessively larger, then you might have problems. One situation where we've seen it an issue is when under backup conditions, the generator, maybe there's a generator used for backup power and they leave all of the connected load, which the generator could not handle, that is supplied by the variable speed drives and harmonic filters. In those cases, we have to be careful to make sure that the generators can handle it. Another question is just saying that do we have a voltage boost at the output of the Lineator? There is a slight voltage boost. The capacitors under lightly loading will introduce some voltage boost, but we keep it within the range of 2 to 3%, where it's the highest at no load conditions, and that is significantly less than any competitive filters on the market. And only if the supply voltage is very near the VFD's max voltage rating would that amount of voltage boost introduce a problem. I have a third question here. It's asking about the fact that I mentioned that the filter can protect the variable speed drives from transients, and it's asking for further explanation of that. Basically, this characteristic of our filter was discovered after we were asked to provide a solution for AC drives failing on an offshore drilling rig, and that's the example that I showed in the webinar. We wondered if the capacitor would help support the voltage drop and filter the ringing effects. And through modeling, we have a solve simulation software that provides modeling of applications for variable speed drives with or without filtering. When we simulated to create an overvoltage ringing condition by adding power factor correction capacitors and introducing a resonance condition, we found that downstream of the filter, even though we have this ringing and overvoltage on the upstream side, downstream of the filter, it was substantially greatly reduced. So we then took that, armed with that knowledge, we applied it on the application on the drilling rig, and I've had many successful applications since then in using it not only to reduce the harmonics introduced by the load it's connected to, but also to protect that load, and more importantly, to protect that load from the distortion on the bus due to other connected loads. So I don't see any other questions. So if there aren't any others, then maybe I'll pass the mic over to Trish so she can close. And I just want to personally thank you myself for taking the time and allowing me to share some information with you on power factor correction.
Great. Thanks, Tony, and thanks everyone for your questions, and I hope you enjoyed the webinar, and I hope it's been helpful for you. If you do have any specific questions, don't hesitate to contact the team. The information is there on screen, and we will be sending you a recording of today's webinar, so if you want to review any of the details more specifically or share with any of your colleagues, you're welcome to do so. And again, a reminder for those of you who do require documentation for your professional development hours, just email us there at the address mirrisinternational.com, and we'll send you the certificate of participation and a test to complete. So thanks very much, and have a great day.